Hello everyone. Today we are going to talk about a very important concept in in number theory, in modular arithmetic specifically. It is called the order, and what is order, and why we come up with this concept. The observation is we see it is very good when we can raise, for example, it's very good when we can the power raise a to the power of, for example, n, and it is equal to 1 mod p. This is very good because 1 is the identity in our number system. It's very good to get a 1, and 1 we like 1, right? And we find out that for different p, n is also very different. For example, when p is equal to 3, uh, 1, of course, 1 is 1 to the power of n is equal to 1, so we don't consider this. But when a is 2, we know that 2 to the power of 2, which is 4, is equal congruent to 1 mod 3, right? So this can be true, and yeah, that's reasonable because we know that um 2 to the power of 3 minus 1, because 3 is a prime, according to Fermat's little theorem, should be congruent to 1. And let's think about p equals 5. P1, of course, we don't consider. 2, how about 2? 2 to the power of 4. 2 to the power of 2, 4, 8, 16. 16 is equal to congruent to 1 mod 5. 2 to the power of 4, right? And it's again the famous little theorem. And 2 to the power of and 3, about 3. 3, 9, which is 4, 20. We know that 3, 9, 27, 81. 81 is the right one, right? It's not another, again, famous little theorem. And about 4 square 16 is equal congruent to 1 mod 5, right? So we see here it is kind of like for every a there exists an n, but n is different, and the maximum is p minus 1 because of the famous little theorem. Kind of, right? This is our observation. So we define, but another thing that is worth mentioning is 4 to the power of 4 is congruent to 4 to the power of 2 to the power of 2 is also congruent to 1 mod 5. And so we see that for every 4 to the power of 2k is always congruent to 1 mod 5. And here is our observation, because if we have a 2 and all the multiples of 2 is our desired form, we can kind of define the smallest one. We kind of examine the smallest one, some property about the smallest. So here is our definition about order. What is order? The order is, this is our key formula, and the order of A mod P is the smallest n. Is the smallest n such that this equation holds, right? And yeah, that's the definition of order. Then we can think about, observe if there's any related property of order, then we can prove. As we've mentioned, we find out that if n is the order, we know that ak, any basically any exponent of an is exponential of an is also mod 1 congruent to 1 mod p. And so here's the case. If we find out large n, and if this is also congruent to 1, can we conclude that the order divides the larger n? And it turns out this is true. And this is what we term the exponential equation into divisibility property. And divisibility is great. We like them. We like them in number series. So this is how order is useful, because if we got an an congruent to 1 mod p, we can get some divisibility property. So what we've mentioned is the most important aspect in order. This is called the fundamental theorem of order. We have fundamental theorem of algebra, of calculus, of arithmetic. Now we have the fundamental theorem of order. And what is this? It is for given prime p and for a that is not divisible by p, we can have, if a to the power of n is congruent to 1 mod p, if and only if the order of a mod p divides n, which is what we've talked about. How to prove this? It's very simple in this direction. When the order divides n, we know that the order essentially say we can always write down what order implies in modular arithmetic form, which is the order a to the power of the order is equal to congruence to 1 mod p. And yeah, if this divides n, then we know that the order times k will be n. If we can write down n like n as order times k, because order divides n. Therefore, we can write down this expression, and we know that the order to the power of a to the power of the order is congruent to 1. So a to the power of the order to the power of k should also be congruent to 1. And this is a to the power of n. So we prove this in the first direction. And let's talk about the second direction. The second direction is when we know an is congruent to 1 mod p, it can imply that the order of p, order of a mod p divides n. How to do this? Maybe we can write down again. We write down order as a modular arithmetic form because it's better to see. We are more familiar with this. This is a modular arithmetic. This is two equation, right? We've proved something related. When we see, I don't know if you remember, but we can use Euclidean algorithm to prove. This implies the GCD of n and order is also congruent to 1 mod p. This can be directly shown by the Euclidean algorithm, and we are not going to talk about this here. But this is true indeed. When this is true, we know that GCD should divide the order, right? This because the GCD divides one element of the element in bracket, and if the GCD divides the order, it means that the GCD is less than the order, less than or equal to the order, right? But if the GCD is less than the order, then we got a new order. We got a new order. A to the power of GCD is congruent to 1, and GCD is it's a new order which is less than the order, and this contradicts with our condition. So GCD has to be equal to the order. What this means is that GCD, this only holds if the order divides n. Then we have GCD n and the order is equal to the order, right? So we've proved that the order should divide n, and we finished the proof. But if you don't know this, we can prove this in another perspective. So this is the first way to prove. The second way is essentially the same, but in another perspective, in a Euclidean division perspective, because we see that the order a to the power of order is congruent to 1, and we kind of like, this is very good, we like this, and we know that n is kind of greater than the order. Therefore if we can split n out into Euclidean algorithm, and we know that, and if we write it like this, we know that the order is congruent to 1, so we left with NAR mod P. But to be specific, what Euclidean division implies is n is equal to order time p time q plus r, right? And r has its bound. R is smaller than order and greater or equal to 0. But here is the case, because an is congruent to 1 as this is a condition. So AR is a to the power of R is congruent to 1 mod P. And here is another order, and this order is strictly less than the previous order, which is contradicts with our condition. Therefore, we can imply that R has to be equal, has to be 0. And when R is 0, we prove that n is equal to order time q, and this is order divides n, and this is another way to prove the fundamental theorem of order. And next, we can talk about some basic conclusions about the fundamental theorem of order. It is due to, because we've observed many times, we have a very powerful famous little theorem. This implies a to the power of p minus 1 is congruent to 1 mod p for many except a p divides a, but we didn't consider this condition. So those situations, so this holds. And according to the fundamental theorem of order, we know that every order half of modular p has to divide p minus 1 according to the fundamental theorem of order. And this is another very important condition because we get a divisibility condition through order. And let's have some exercise. And this is too much in the one video, and I will split it into another video. And yeah, that's today's video, and see you next time. Thank you.